Now, of course, one example of lightweight aggregate concrete is the dome of the Pantheon, okay, where the naturally occurring pumice was used as part of substitution of normal aggregate to reduce the weight of the dome. So, you know that there is no reinforcement in the structure. This is a concrete dome, and it was built, I forgot the time period, 500 AD or something, I am not sure, not perfectly clear about the time period, but yes, there is a usage of low density or lightweight concrete in the dome of the structure. So, synthetic lightweight aggregate includes, as I said, expanded clay or shale or slate. What you basically do is heat it to a temperature which causes bloating. Basically, air is entrapped in the system because of the layered or foliated structure, right, and possibility of even gases that are released by organic materials that are present already in these shales, and because you have organic deposits, when you extract shale or clay, there will be some organic material present, and when you heat that to a very high temperature, the gases will form, get entrapped in the system, and that leads to a higher porosity, causes the material to become lightweight. Okay. Then the process also leads to an impervious coating to form on the surface, which prevents the escape of this gas. That means the bloated structure is maintained when you do this heating process. So, you still need to provide energy to get this lightweight aggregate. You are forming after provision of a high amount of energy. Expanded slag, as I said, you trap steam in molten slag, right. The steam basically generates high pressure vapor inside the system, and that leads to a foaming of the system. Okay. Now, as a result of the steam, apparently it renders the material inert in a cementitious system. That means it is not going to be reactive anymore, it is going to be just a expanded slag as a aggregate. It will not be as reactive as blast furnace slag, which is quenched. Okay. Sintered fly ash, as I said, it is caused by pelletization of fly ash particles. You have to bind the particles together, typically using clay or cement, or like clay like bentonite. It can be used to bind the fly ash particles together. The pellets are formed to aggregate size, and then these are fired in a furnace to a temperature that leads to the sintering, like the formation of a brick, for instance, right. So, water can evaporate, carbon combusts, and fly ash particles coalesce by forming the ceramic bond between the silica and the alumina. Perlite is essentially volcanic glass. It contains 2 to 6% water in the bound structure, and again this has to be heated rapidly to 1800 degrees Celsius. So, perlite is a foliated volcanic glass. So, when you heat it to 1800, that results in steam that encapsulates air inside the system. Sorry, perlite is not foliated, vermiculite is foliated. I keep getting confused. Perlite is essentially volcanic glass, okay, which you can then expand by heating to a temperature of 1800 degrees Celsius. And vermiculite is a foliated platy clay. The interlayer water basically turns to steam and causes exfoliation, separation of these individual plates, and then the overall material as an aggregate becomes extremely light in weight. Okay. Up to 30 times the original volume can be actually obtained by doing this process of heating to 1000 degrees Celsius. So, as you primarily see, all of these systems are formed by supplying a significant amount of energy to heat. That is why using lightweight aggregate is not always very sustainable from the point of view of actually using something natural versus making something lightweight by enhancing or rather providing the heat energy to it. At the same time, there are applications where we cannot do without lightweight aggregate. If you really want extremely low density concrete, then using lightweight aggregate, if it is available at a cost that can be justified, is a good idea. Otherwise, you have to obviously deal with using air entrainment or using foaming or aeration to really get the low density which is possible. Okay. Perlite and vermiculite are primarily used in insulating concrete and for protecting steel against high temperatures and fire. So, when fire happens, obviously the concrete is a protecting layer to the steel, and when you have a system that is providing a very high insulation, the heat conduction to the concrete is slowed down significantly. So, the longer the heat takes to reach the steel, the longer the structure will be stable. Okay. So, insulation also helps against fire damage that happens in buildings. Now, you can also use thermocol or expanded polystyrene, that is another way of reducing weight. Sawdust is again a filler type material which could be again used to make lightweight concrete. Now, lightweight aggregates have high porosity, so obviously they will have very high water absorption. You need to change the mixing process, because if you put the lightweight aggregate in a dry fashion inside the concrete mix, it is going to absorb all your mixed water, and you really do not know how to then control your workability. So, generally when lightweight aggregates are used, there is a pre-soaking that needs to be done. You pre-soak them and make them saturated surface dry before you utilize them in concrete. Okay. And in some cases it may be difficult to measure the absorption, because the porosity in these materials is so much, because to measure absorption you need to get the aggregate in a saturated surface dry state. What is saturated surface dry? When all the pores of the system are filled with water, but there is no water sticking to the surface. Now, that is very difficult in a system that is very porous, because as soon as you remove from the water, the pore water also will start draining out. Okay. So, getting SSD condition is not very easy. So, measuring absorption is also not easy. Now, strength of the aggregate, how do you determine strength of an aggregate? What kind of experiment do you do? You do the impact and the crushing test, right? Essentially, you take a sample of the aggregate and you have this hammer that drops, and then you measure how much of the aggregate is still retained beyond a certain size, right? So, that is the strength of the aggregate. When you use it in concrete, how does the strength of the aggregate affect the strength of the concrete? Does the strength of the aggregate affect the strength of the concrete? It does. How? In what type of concrete? If the concrete is of low strength, what will happen? Will the aggregate come into picture? Yes or no? No, right? Because in low strength concrete, the cracks pass through the ITZ. When you make the concrete stronger and stronger, the ITZ becomes strengthened, and then the cracks can pass right through the aggregate. We discussed this, right? When you do high strength concrete, your cracks are passing through the path of least resistance, and that happens to be the aggregate in the case of high strength concrete, and that causes the failure to be highly brittle, explosive, and that is something that you can also expect will happen when lightweight concrete is used or lightweight aggregate is used, because lightweight aggregate will in general be much more weaker as compared to the paste phase, right. So, in such a case your concrete will fail through the aggregate, right. But the crushing test or impact test that you do for normal aggregates, you cannot really do for lightweight easily, because unless your lightweight aggregate is of the type of sintered fly ash or expanded clay and all, which may have some strength in it, all other aggregates may just get crushed to powder when you do the impact test or crushing test. So, you need to adopt the tests carefully for lightweight aggregate. Now, segregation can happen in the opposite direction, because if you are using perlite or vermiculite as aggregate, for instance, this can actually start floating to the top. In normal concrete, aggregate settles, paste floats to the top. Here opposite can actually happen. So, you need to design your concrete mix well for that purpose. So, some properties of lightweight aggregates are given here. So, the densities and the absorption levels that you can actually get, and how the aggregate is obtained. So, processed natural PN, S is synthetic, N is natural. So, pumice and crushed stone obviously is natural. Some types of natural aggregate that you can actually, this is just natural aggregate. Crushed stone is just listed for comparison of the properties. This is the bulk density of the crushed stone, which is typically of the order of 15 to 1600 kilogram per cubic meter, and absorption of crushed stone is usually less than 1%, right. Most granite, limestone will have an absorption of less than 1%, but as compared to that, you can see the extent of absorption of some of these aggregates. For instance, perlite 10 to 50%, you can get up to 50% water absorption in the system. Okay. So, varying properties of these materials are there. You need to choose your material carefully to design the concrete with lightweight aggregate. That is why lightweight aggregate concrete is a lot more complicated than producing foam concrete or aerated concrete. Okay. Aerated concrete is something we will talk about, we do not discuss that yet. Just an example of a fly ash aggregate. So, you have these pelletized fly ash which has been then fired inside a furnace at very high temperatures to cause sintering, right. That is why these are rounded, because they are pelletized. So, pellets are nice and round. Okay. You can see that there is also a commercial product called Light-Ag that is actually available for sintered fly ash aggregate, right, and this is available in the market. But then again, it is produced by pelletization and sintering, both involving energy imparted to the process. So, is it really worth putting in that much to obtain fly ash as an aggregate? So, as I said, most of these lightweight aggregates are produced by imparting a significant bit of energy. So, you have to do a complete LCA analysis to really get a clear picture of whether it is justified to go with lightweight aggregates at all. But for certain applications, as I said, you do not have any other choice, you have to go with lightweight materials. Now, fly ash aggregates can, of course, as I said, you can form by sintering. You can also form the same by cold bonding. Now, what is cold bonding? If the fly ash is reactive, right, if the fly ash is reactive, extremely reactive, it can react with calcium hydroxide at ordinary temperatures to form CSH, right, because fly ash is after all reactive silica. If it is highly reactive, it can react as well. You can make a mix with calcium hydroxide, do the pelletization with calcium hydroxide and just cure the material, that will also form hardened aggregate because of the reaction of fly ash with calcium hydroxide. Alternatively, if you have type C fly ash, what will happen when you have type C fly ash? It will exhibit much higher reactivity because of the higher calcium content present in the system. So, with type C fly ash, often cold bonding is a realistic solution. Now, this is good because now the energy is only for pelletization. The remaining process is just natural curing. There is no high temperature sintering involved. Okay. So, that is one thing which you need to consider. Can you process the material without provision of the high temperature sintering? And that is what you can do with cold bonding if the fly ash is reactive. Now, oftentimes to increase the rate of this reaction, you can also do autoclaving. Autoclaving implies putting the material in a chamber where pressure and temperature can be increased to increase the degree of reactivity that you find in your system. So, it is almost like steam curing, but at high temperature, or steam curing at high pressure. Steam curing is normally done at atmospheric pressure, but autoclaving means steam curing at high pressure. You also pressurize the chamber while doing the curing. Again, here there is a influence of the different types of binders that are used for sintering the fly ash aggregate, or to pelletize the fly ash aggregate, right. Depending upon the type of binder that you use, either bentonite or cement or lime, the resultant sintered aggregate that you produce will have a different property. For instance, if you use lime, the resultant sintered aggregate still has a fairly high water absorption. If the binder is cement, you are lowering it to a certain level, but bentonite seems to work quite well in terms of water absorption characteristics. You are adding about 20% sodium bentonite to the fly ash and then causing pelletization and then sintering this material, and that leads to a significantly low water absorption. So, type of binder that is used to pelletize, because you need some glue, no, to keep the fly ash particles together to make the pellet, and then these pellets are sintered, and then you get the properties of lower water absorption. As I said, cold bonding can be done with fly ash aggregates that are reactive. So, again, depending upon the type of curing method, you can actually get different properties. If you are willing to wait for long, normal water curing is the best. The next best is autoclaving, and the last is steam curing. Okay. Natural bonding happens over a long period of time, but then you get a property of water absorption that is much lower as compared to what you get from autoclaving or from steam curing. Okay. So, generally what you end up with normal curing is that you get a much more denser microstructure that forms. We discussed this when we talked about steam curing and its effects on the long term development of strength. When you do accelerated curing, what ends up happening is you introduce more coarse porosity in the system, and that is what exactly you can think about the cold bonded fly ash as a hydrating cementitious system, right, the same thing. If you subject that to high temperature curing, it will gain strength fast, but it may not have a long term property that is matching that of normal low temperature curing. So, same concept here also. So, this is just some data that is presented from the work of Manikantan, who worked on his PhD here with respect to fly ash based aggregate system. Now, the interesting part about the work that has been done here is that this is not just based on the fly ash that you actually get from the ESPs, it is also based on bottom ash and other low quality fly ash that is usually dumped in power plants. In most power plants, they have these ash ponds where they dump the fly ash that has not been collected by cement companies to make blended cement. A lot of that extra fly ash is just dumped, and now there is also tons and tons of this fly ash that is actually available, and Professor Ramurthy's group has actually worked with this low grade fly ash also to a large extent and ended up producing very good quality lightweight aggregate from the system. Okay. So, finally, the other part of lightweight concrete is aerated concrete. Aerated means you just generate air in the system or entrap gas in the system. So, here what we do is we use aluminum powder for generating hydrogen gas. So, in an alkaline system, when you have calcium hydroxide present in the system, the presence of aluminum, not aluminum oxide will be mostly inert, it will not do anything, but aluminum itself as an element, if it is present, it will react and lead to the generation of hydrogen gas. And if that happens, the gas gets entrapped in the system and that leads to the aeration of the system. It is almost like baking a cake, right. What do? What do you add to aerate the bread? Yeah, you can add baking soda or natural materials, yeast is also there, which you can add to bake, right. And then when you add this and cure it at a high temperature, you create a system where the air is entrapped inside the dough, right. So, your bread basically has, bread is aerated, aerated flour, that is what bread is, right, aerated cured flour. That is exactly what we do in the case of aeration of concrete also. So, that is why we do not want to use aluminum pipes to transport concrete, right. Aluminum pipes will be much lighter in weight, easy to handle, but you can't use them because if a concrete is pushed through aluminum pipe, you start generating hydrogen gas and that will block, because when air voids are present, you can't really pump the concrete well, right. So, now exact same reason why we do not use aluminum pipes is the reason that we use aluminum to generate hydrogen gas inside the system. So, what you do by entrapment of this gas inside the system is generate a porosity of nearly 30 to 40%. Significant porosity can be generated. And to accelerate the heat development, accelerate the strength development and to increase productivity of making these blocks, you can do autoclaving, high pressure steam curing. That is what autoclaving is, that is typically done, and the blocks that are produced are called AAC blocks or autoclaved aerated concrete blocks. These are today perhaps the most commonly used concrete blocks everywhere in construction. As I said, you can have a block of typically 200 by 600, that is the typical size of these blocks. What is the size of a brick? Yeah, so essentially 100 by 100 by 200. So, now you can see how many blocks are there, right, 2 into 2 into 3. So, 12 blocks, 12 bricks per block, volume of 12 bricks comes in one block, and this block is fairly light in weight because of the lightweight concrete nature. So, you can actually have one worker put this in place. There is a single mortar joint, right. So, it increases productivity significantly. Instead of lifting 12 bricks, now you are lifting 1 block, right. So, again you need to pay attention obviously to the magnitude of the aluminum that you add. If you have dosage less than 0.1%, you do not really get deviation. At dosage of more than 0.2%, you generate too much air in the system. And if you generate too much air in the system, the bubbles are not going to be stable, they will start breaking. The bubbles have to be of a proper size to be properly entrapped and remain stable in the system. Okay. The air generation will also depend on fineness of the aluminum powder that you use, okay, and the alkalinity of the solution. Higher alkaline solutions, just like in the case of foam concrete, a higher alkalinity also helps in the case of stabilizing the air void system in this aerated concrete also. Okay. Temperature of the alkaline solution and liquid to solid ratio overall for the concrete mix can also affect the aeration. So, several different factors, most of these are well covered in the literature that is produced from IIT Madras.